Okay, so video 3 on elastic collisions in 2D. Here's a question, have a read, pause the video, give it a go, and then unpause and watch my solution when you've given it a go. Okay, so hopefully you've had a read through the question. So we've got two smooth spheres, P and Q, okay? They have two different masses, 0.3 and 0.2 kilos, and they have two different initial velocities, 4.2 and -3.1. They collide in two dimensions, okay? And when they collide, their line of centers is parallel to I. So this start of the question, sort of this chunk here, okay, gives us more than enough information to do a diagram, okay? So let's get this diagram sorted, okay? So they almost always look the same, okay? Which is two spheres right next to each other. And in this case, they're coming in from the bottom like this, okay? And they're gonna be colliding and leaving at some velocity, let's say something like this. Now, I don't know this for a fact, okay? They might not end up moving like this. However, for my diagram, I'm just going to guess these two directions, because if my maths gives my numbers coming out as negative, then I would know they're going in the opposite direction, okay? So that's an important thing. Ignore that, sorry. Okay, so let's have a look. Well, we know that the initial velocity of P, I'm going to draw P as a left one, by the way. The initial velocity of P is 4.2. And the initial velocity of Q is -3.1. Now, we know the J components of their velocities are not going to change because they're moving and their line of centers are in the I direction. Okay, so this is in the I direction. So the components of the velocities perpendicular to the line of centers is never going to change. So this one has a J component of 2 and no impulse acts on that J component. So that stays as 2, and likewise this stays as 1. Okay, so we can always do that in 2D collisions, okay? The J components will never change if the line of centers is parallel to I, okay? If the line of centers is parallel to J, then the I components wouldn't change. Okay, now we don't know these two I components of the final velocities, and that's what the whole question sort of is centered around. So I'm going to just call them X and Y, okay? Well, that's what mathematicians often do, and they don't know things. So let's call them X and Y. Now, what we can do, okay, is because we know no velocities are changing perpendicular to the line of centers, we can just turn this into a one-dimensional problem like we did in the previous section of the textbook. Okay, so we know this is P with mass 0.2 and this is Q with mass 0.3. Okay, and I've done the masses the wrong way. Okay, P has mass 0.3 and Q has mass 0.2. So they're moving towards each other, and now we're just looking at the I components. We're just looking parallel to the line of centers. Well, P is moving to the right with speed 4, and Q is moving to the left with speed 3. Okay, so these are our two arrows, and these are our two balls. Okay, it is -3. However, we've taken the diagram to the left, so it's +3 to the left. Okay, so we are just going to keep that as +3. And we've just assumed that X and Y just act to the right like this, okay? If we were to get X or Y come out as negative, then we just know they're acting to the left, okay? That's all that it means, okay? So always just, I would always assume they're moving to the right, okay? Because it just makes you really familiar when you do questions, okay? So always assume they're moving to the right like this. So we're going to do PCLM, okay, the conservation of momentum on these two spheres, just like we did in the previous section in 1D collisions. So 4 times 0.3 minus 3 times 0.2 is equal to 0.3x plus 0.2y. Okay, so this is a conservation of momentum. Okay, the momentum of this ball take away the momentum of this ball initially, okay, because they're moving in opposite directions. That's this is equal to the final momentum, this. So let's sort this out. 4 times 0.3 is 1.2. Take away 3 times 0.2. So that gives us 0.6 on the left is 0.3x plus 0.2y. And we'll times everything by 10 to tidy it up. 6 equals 3x plus 2y. Now, there's one equation that we have. However, we've got two unknowns of one equation, so we're not getting very far just using that. So now we have to use this second fact here. Okay, the kinetic energy, let me highlight it. The kinetic energy of Q immediately after is half of the kinetic energy of Q immediately before. So we know that the initial velocity of Q, UQ, is given by -3.1. Okay, or -3i plus j. And we know that VQ is given by y1. Okay, that's what we've defined it as. So the actual magnitude of the initial velocity of Q, okay, the magnitude of UQ is a square root of -3 squared plus 1 squared, or just root 10. Okay, and the magnitude of VQ is a square root of y squared plus 1. Okay, so if the kinetic energy of Q after is a half of the initial kinetic energy of Q, let's turn that into an equation. So the kinetic energy of Q before is a half times the mass of Q, let's have a look, 0.2 times the initial velocity of Q squared, so that's root 10 squared, so 10. And we know that that times by a half is going to give us our final velocity, which is a half times the mass of Q times the final velocity of Q squared, which is just going to be y squared plus 1, because the square and the square roots cancel out. Okay, so now that we've got this nice kinetic energy equation here at the bottom, okay, we can use this to solve for y, because as you can see, y is the only variable in here. And then once we've got y, we can use this equation to work out x. So let's have a look. Okay, well, the first thing to easily notice is that the half times 0.2's cancel out. So what do we get? A half times 10, so 5, okay, ignore my black pen, 5 equals y squared plus 1. Y squared equals 4, so y is equal to plus or minus 2. However, okay, this is where we need to sort of just use our brain a little bit, okay? If we look here, okay, if y was minus 2, that means this final velocity would actually be going in, I'm going to do it in red, in this direction here. Okay, and is that possible? Can Q start moving along the plane in this direction and then just carry on moving in this direction? Well, no, because the spheres would have passed through each other. Okay, that's the important thing. That can't happen. The spheres would have passed through each other. Okay, and that's just not physically possible. So it can't be -2. Hence, the final velocity in the x direction has to be +2. So we're only going to take the positive root, because if y equals -2, spheres pass through each other. Okay, so we have to take the positive solution. So let's go back to our diagram. Okay, we now know that y is +2, so 2. Now we can use this equation that I've boxed up here to solve for x. Okay, so we know 6 equals 3x plus 2 times y, which is 2. Okay, and we'll solve for x. So 6 take away 4 is 2 divided by 3, so x equals 2 over 3. Okay, solving this equation for x. So 2 over 3, and we happen to have guessed the right direction because 2 over 3 is positive and we've guessed that it's moving slightly to the right. So this is our diagram here after doing all of this maths to work out the final velocities. Okay, so I've cleaned up my diagram a bit and got rid of all the working. So here's sort of the key information, and now let's actually see what they're asking for in the question. So they want the velocity of p immediately after. Well, we've worked that out. Okay, that's this vector up here. Okay, so 2/3, 2, and that's the velocity of p after the collision. And the velocity of q after the collision in the very much the same way, that's just 2, 1, okay, which is vq, and that is this velocity over here. Okay, and then the coefficient of restitution. So to find the coefficient of restitution of a 2D collision, we only ever look in one dimension parallel to the line of centers. So like we did down here with our PCLM, okay, but instead of using PCLM, we're now using Newton's law of restitution, or Newton's experimental law, okay, and that's that E is equal to the speed of separation over the speed of approach. So what's the speed of separation? Well, it's 2 take away 2/3 because they're moving away in the same direction, and the speed of approach, okay, is 4 plus 3 because they're moving towards each other, okay, and that's going to give us 4 over 21, I believe. Yeah, that should be about right. So E is 4 over 21. And for the last bit of the question, it says find the size of the angle through which the direction of motion of P is deflected. So if we look at the initial velocity of P, it is moving in this direction, and if there was no collision, it would just carry on moving in that direction of the green vector I've drawn. Okay, however, there was a collision and the final velocity is moving in the red direction. So what angle is it being deflected through? Well, it's being deflected through this angle between these two vectors that I'm going to call theta up there. Okay, now we've got two vectors and we want to work out the angle between them, so we're going to be using the dot product, and that's always what I recommend doing in questions like this. When you're finding an angle of deflection, it's a very common question, use the dot product. Okay, so what's the final velocity of P? Well, it's 2/3, 2, and what's the initial velocity? It's 4, 2, okay, and that's UP. So we've got our two vectors, and now we just want to work out the angle between them. Okay, so UP dot VP equals mod UP mod VP cosine of the angle between them. So 4, 2 dotted with 2 over 3, 2 equals the magnitude of UP. Okay, well that's just gonna be the square root of 4 squared plus 2 squared. Okay, the magnitude of UQ, okay, that's 2/3 squared plus 2 squared. Cosine of the angle between them, theta. So let's work this out. So dot product on the left is going to give us 8/3 plus 4. And on the right, we're going to get the square root of 4 squared plus 2 squared. Okay, that's going to give us 2√5. And the square root of 2/3 squared plus 2 squared should give us, so 2/3 squared plus 2 squared, 2√10/3 times the cosine of theta. And if we divide both sides by this product out here in the front to get cos theta by itself, okay, we're going to get that cos theta is √2/2. And that should ring a bell. That theta is going to be 45 degrees. Okay, very nice number there. Okay, sort of confirms that we're right if we get a number that nice.